Yeah, I guess we can probably get started then. Hello, everyone. Welcome to the first edition of RoboLaunch, the Launch into Robotics initiative. So you might be wondering, what is RoboLaunch? So essentially, RoboLaunch is an outreach initiative geared towards inspiring participants across the world to participate in robotics. And it's aimed towards diversity, equity, inclusion, and belonging, where we're trying to create a sense of belonging to the robotics community and make it more diverse. In RoboLaunch, we essentially have multiple components, including a seminar series, workshops, competitions, and community building. And through the seminar series, you'll be going through a wide variety of interactive robotic talks, exploring skill building, connections, career journey, different topics in robotics, applications of robotics, and other things. And for the workshops, we have interactive sessions planned on specific topics in robotics, for example, computer vision fundamentals, motion planning, controls, RL, product management, and many more topics. And we also have a tentative competition for fall planned, where it be a learn and teach style competition where you can get to show us what you've learned across the summer. And we also have community building through Discord and other various mediums where we plan to promote an inclusive community on robotics. So for the seminar series, we have a diverse set of speakers across the summer who will be talking about our various set of topics, ranging from application of robotics to how research and education can be fun. And RoboLaunch was made possible by a large number of organizers and also members from the RIS and RA community, and a huge shout out to them. I guess I'll now invite Rachel to talk about RIS and RoboLaunch. Thank you.
Thank you, Nikhil. Hello and welcome. My name is Rachel Burson, and I serve as the co-director of the RI Summer Scholars Program. This is really a wonderful opportunity for us to come together. CMU's Robotics Institute community is committed to working towards lowering barriers, increasing accessibility of futures in robotics. In 2006, we launched an undergraduate research program, coupled it with professional development, scholarships, and guidance. And we've been working with scholars from around the world to build knowledge, skills, and a network to open doors for years to come. And over 80% of our scholars go into grad school in roles in which they're impacting the robotics sector. RIS is community and alumni driven. Each year, over 100 members of the CMU and extended community help to shape this core outreach program, which is an immersive research program. So core to our values are inclusion, efforts to increase access and participation in robotics, and RoboLaunch grows from this tradition. Over the last half decade, we've also been hosting in-person and online opportunities for students and teachers to learn about robotics. We're especially proud that RoboLaunch is alumni shaped and driven. More opportunities will be announced, as Nikhil noted at the beginning, to explore robotics. There will be workshops, opportunities to share through the Discord, and we'll also be connecting with colleagues from the Robotics Institute that are launching a website with a series of curated robotics resources. So stay tuned, there's much more to come. This is really about sharing our passion for robotics. This is about trying to give back to all those that have created an opportunity for us to host the RIS and other programs for the last decade and a half. We'd like to thank all of the Institute labs, faculty, students that share their knowledge and expertise and passion every single summer to make this possible. And we're excited to be joining and connecting and hearing from colleagues from around the world that share this alignment of wanting to make more bridges into robotics. And we're excited to kick off today with that. This opportunity is made possible by the TC Energy Foundation, and we thank them for their generous support that's going to allow us to increase access and share more broadly what we're doing here in robotics. I'd like to introduce Dr. John Dolan. John will be introducing our speaker today. John is a faculty member of the Robotics Institute and a researcher. He focuses on areas of autonomous driving, telesupervisory human-robot systems, and robot reliability. In addition to being a noted researcher, John is also committed to education and increasing opportunity. He's a member of the Argo AI Center at CMU, and John has mentored a number of undergraduate and high school students over the past decades. John serves as the director of risk and also direct a graduate program and spends an enormous amount of time dedicated to both education and research. So I'd like to welcome John Dolan, who is with our current group of risk scholars, to introduce our first speaker of the day.
Thanks very much, Rachel. It's my distinct pleasure to be able to introduce our inaugural RoboLaunch speaker, Professor Liam Paull. He is at the University of Montreal and heads up the Robotics and Embodied AI lab there. And his lab focuses on a number of things, including building representations of the world, such as with SLAM and modeling of uncertainty. He spent time earlier at MIT's CSAIL Artificial Intelligence Lab, and also has a lot of experience in marine robotics and underwater robotics. The last thing I'll briefly say is that he's a co-founder and director of the Duckytown Foundation, and I think today he's going to be talking more about that in detail, so I won't say anything else. That'll pass it off to him. It's a pleasure to welcome you to the RoboLaunch series.
Thank you, John and Rachel and Nikhil and all of the organizers for organizing this and for inviting me. It's really an honor. I'll also say right off the bat, I really like getting interrupted. So if there's questions in the chat for the folks who are on Zoom or the folks who are in the classroom with John, please don't hesitate to interrupt me. So yeah, the talk is about Duckytown and the AI Driving Olympics. But I thought since I'm the first speaker in this series, that I would start maybe from the beginning, just so that we can kind of all get on the same page. Maybe some of this might seem obvious, but some of it maybe not. So what's the real state of the art right now in robotics? Is it this? Is it trucks that drive themselves down the highway and deliver beer? Is it robots that can clean up our houses or dumps? Is it autonomous vehicles that can drive blind people around seamlessly? Unfortunately, this is not quite the state of the art of robotics right now. It's kind of closer to this. So on the left-hand side, we have some of the blooper reel from the DARPA Robotics Challenge, which is now admittedly a few years old. So it's maybe not the state of the art, but nevertheless represents some of the distinct challenges. And on the right, we have, and I mean, there's been sort of a long history of accidents and tragedies that have been associated with autonomous driving. And this is maybe one of the most famous. It's an incident that happened in Tempe, Arizona, where an autonomous car that was in testing hit a pedestrian, and this was the first pedestrian fatality. So it's a long road. It's a difficult problem, and we have a long way to go, and sort of like maybe don't believe the hype. But we're all passionate about it, and we want to make it work. So let's see, what can we do? Maybe we'll start off with thinking about actually what is a robot. We probably all have like different conceptualizations of what is a robot or what the definition of a robot is. And I don't think that it's necessarily important that we have a very well-defined thing, but I can throw up some examples like, is this thing a robot? Or are these things robots? This is some kind of manufacturing setting where these robot arms are helping to weld and assemble cars. I think probably most people would say that, yes, these are robots. How about your dryer? Is your dryer a robot? It like has a thing that moves and turns around, and maybe some of them even have like temperature sensors. How about your toaster? Is your toaster a robot? How far could we push this? I mean, the toaster has got like some kind of actuation in it that allows that little lever to go up and down, and maybe also figures out how toasted your toast is or something. And then maybe the like most clear-cut case, although it doesn't look like our traditional view of what robots look like, is the autonomous car, which I would argue is like definitely a robot. And so maybe we can think about defining what a robot is. And so the origins of the word robot actually come from the Czech word robota, which means forced labor. And this term actually first appeared in this super creepy movie in 1935. And so the conceptualization, okay, I'll pause this. You get the idea. The conceptualization, or the origins of the term robot actually come from more forced labor kind of background. We want these machines that we can tell them to do things and they'll just do things for us. Okay. What about the word autonomous? So the word autonomous means something different than the word robot. So are these things autonomous? And what does that really mean? So let's think about the definition of the word autonomous. And in particular, let's think about it as being distinct from the word automated. So to me, the word automated, so the origins of the word automated come from the Greek word automaton, which means something that acts by itself. So I would argue that all four of those examples are automated systems. The arm that's welding the cars, the toaster, the dryer, and the car. It's able to repeat the same motions over and over with little intervention from some human being. Autonomous is a very different concept, though. The word autonomous comes from the Greek word autonomos, that means something that has its own laws, is somehow self-governing. And embedded in this definition is some notion that there's a choice, that the agent, there's some notion of agency involved. The agent is actually making a choice to take some action. So according to that definition, when we go back and look at these, well, the thing that looks most like a robot, I would say, is this arm, but that arm is not autonomous in any way. That arm is just doing the same repeated motions over and over. The car is clearly autonomous because it has to perceive the world and make some kind of decisions about what to do in the world. The toaster and the dryer are a little bit tricky because it sort of depends on the model of toaster and the model of dryer, because if the dryer has a temperature sensor and it's reading information from that temperature sensor and then deciding when the clothes are dry enough, and then taking the action to stop tumbling the thing around, well, that's some degree of autonomy. That's some level of decision-making that's due to some kind of information that's gathered from the world. Sort of same story with the toaster, I guess. Okay, so what's AI? This other thing that we hear a lot about. So, and then embedded in that, and what's the distinctions between AI and machine learning and deep learning and all these things. So I also don't have formal definitions of these, but I think that we should probably be relatively agreed with the idea that there's this Venn diagram or nesting that we can build. So the artificial intelligence I view as the broadest concept out of all of these three concepts. Anything that is programmed to do something that requires some kind of level of automation, we could probably classify that as artificial intelligence, in the sense that it's supposed to be doing something that seems like it's intelligent to us. Machine learning is a subset of artificial intelligence that's going to leverage data in order to make its decisions in some way, or to build models. So any system that is explicitly using data to build models, I would classify as a machine learning system. Deep learning takes that idea of machine learning and pushes it really as far as you could possibly go. So these deep learning systems now that we've had for the last few years use extremely large data sets and build and use extremely large models with a lot of parameters to build models of things that are very, very hard to model with traditional AI, let's say. Exactly where the limit, where it's enough parameters that a machine learning system becomes a deep learning system, is not clear, and maybe not even really that important either. Okay, question from Sadaf. Essentially something that has a closed loop control. So something that has closed loop control, it's close. It sort of depends. Things can have closed loop control and still not be autonomous. There's something important about the sensory aspect is needed for autonomy. In some sense, you have to be gathering information about the world and then assimilating that information, or maybe assimilating that information into some model and then using that model to take action. That's the bar for autonomy. In terms of automated, so a lot of those arms have closed loop control loops that are operating on the actuators, for example, but those are, I still wouldn't argue that they're necessarily like autonomous systems. Okay. So in the realm of machine learning and deep learning, where we're actually using data, there's different sort of types of types of paradigms and ways in which we can use data to build models and learn to do things, or that we can teach autonomous systems to do things. Kind of the most straightforward and the one that's had the most success so far is this idea of supervised learning. So in a supervised learning system, what we're going to do is we're going to have a data set, which is like a bunch of pictures of cats. And then we're going to ask people to like draw squares on all the pictures of cats. And then those are going to become the labels. And then when we feed that to our model is going to take all these pictures that we give it and all the labels of the cats, and is going to learn this, like how to find cats in pictures. And so the hope here is that when we give the system a new picture that it hasn't seen before, that's got a cat in it, it can extrapolate its understanding of what it's learned about detecting cats to detect new cats in new images. And so this paradigm works fairly well, but if we're talking about robot systems and driving cars and self-driving cars and things like this, the driving a car is not exactly like detecting a cat. And so there's a number of reasons why, but I want to highlight just a couple. So one very problematic thing here is that we're able to trick these supervised learning systems in ways that are very not intuitive to us as humans. So here on the left-hand side, we have cats and dogs. It's a classifier that's supposed to classify pictures as either having a cat or a dog. Here we have on the left, we have 100% confident that the top one is a cat and the bottom one is a dog. And then we just add some kind of like random noise to get these images on the right-hand side, which to you or I, the top one is clearly still a cat and the bottom one is clearly still a dog. But all of a sudden our system is completely confused. So these metrics of uncertainty about how confident the system is might not be super important when you're detecting cats and dogs, but might be super important when you're detecting a pedestrian and you have to figure out whether you need to like swerve to avoid it or not. So the most important thing is like the safety concerns of physically embodied robot systems. And then there's also this issue that we want, like this prickly issue that's like maybe kind of boring, but super important, that in order to get these technologies out into the world, they're going to need to pass like some kind of certification in order to be certified as being safe. And the problem with these types of systems is it's very hard to make to establish any kind of guarantees about their performance, which regulators don't like, let's say. And then there's the problem of now the actual performance of the system is dependent on the data that you gave it at the beginning. So if you gave it really garbage data, then the performance of your system is going to be garbage. Okay, so that's maybe an intro to what are robotics, what are autonomous systems, what are automated systems, what's AI, what's machine learning, and how do these things sort of fit together. So I am mostly interested in autonomous mobile robots, and the autonomous car is kind of like, it's supposed to be this thing that for roboticists, it like takes us out of the shadows and into the spotlight and makes us all superstars because we like solve this really hard problem of autonomous cars. So why do you want an autonomous car in the first place? Well, and I mean, I'll skip over this pretty fast. I think most of the folks in this audience are probably already drinking the Kool-Aid in terms of convinced of the value of such a technology, but it's worth thinking about anyways. So first of all, we waste a lot of time driving. I don't know the age and who has driving licenses in the audience, but the average North American spends 100 minutes per day driving. So that's 38,000 hours in your lifetime. The average North American drives 1.3 million miles in their lifetime. That's more than 3 times the distance to the moon. So if we could somehow recover that time, that would be great. There's also accidents that happen during all of this 1.3 million miles that we do every year. The latest data I have here is 2016, but the trend is actually roughly constant, about 37,000 traffic-related fatalities. But the problem is that we drive so much. So like that number of 37,000 people that died in traffic-related fatalities in the US sounds like a really big number, but it's big numbers working with other big numbers. So because we drive so much, this means that roughly for every 100 million miles that someone drives in the US, there's a little over 1 death. But like, it's hard to even conceptualize how far 100 million miles to drive is. Like, that's really far. So this is the bar that we have to attain in order to certify that our autonomous system is safer. We have to somehow show that we're achieving better numbers than 1.16 deaths per 100 million miles traveled. And even then, it's like, how many million miles would our autonomous system have to travel in order for us to have statistically significant data to actually verify this? Like, very, very challenging. Then there's all the socioeconomic stuff. And I know this is very double-edged. People could lose their jobs, but from a societal standpoint, I think we probably should be able to agree that if less people have to do menial tasks, it's probably a better thing for society. People should be able to allocate their time towards things that are more meaningful in some sense. But I don't really want to get into a big debate about job loss and automated system. That's a whole other talk. And then we saw this video already. There's the potential that some folks who maybe would not be able to drive or get around would not be able to get around. And this was like a promo video that was put out by Google back when they were still trying to hype the project. I see that there's a hand raised, but I'm not sure what to do about that.
I think you can probably go ahead. I think it was random.
Okay, so for any questions, I'm happy to take. Okay, so what are the tools that we can bring to bear to build autonomous cars? So I've got this diagram up, which I think represents roughly the structure of any traditional robot system, particularly before the invention of machine learning. So, but we'll use the autonomous car as an example. So an autonomous car is pictured at the bottom right here. It has sensors like cameras, and these weird looking things are like LiDAR that shoot laser beams out and measure how long it takes for the LiDAR to hit something and bounce back. This outputs this huge stream of raw data, and we need some kind of system that takes that raw data and makes some sense of it for us. And I'm referring to that here as the perception system. So here, maybe it takes a picture of a road scene and characterizes each of the different things in the road scene according to different classes, like purple is road and green is people, etc. So still, we're getting this, this perception system is running at maybe like 10 hertz or 30 hertz or something, still outputting a huge amount of information. And what we need is we need to assimilate all of that information into one kind of coherent model of the world. And here I use the word estimation for that, but you could have lots of other words that could describe this thing. So we're going to take all of the output from this perception system and we're going to put it all together, and we're going to try and build a world model that's going to contain all of our information about where all the people are, where all the road is the drivable area, what people are likely to do in the future, whether it's about to rain, whatever we deem to be important for solving the particular task. Then once we've got that model of the world, we have some kind of task that we're trying to achieve, for example, like driving. We take that model and we take our task and we build some kind of a plan about how we're going to actually execute that task. So in the driving case, that might be like, I'm going to drive along this path, down this road, and I'm not going to hit anything. And then that gets further processed by some kind of control algorithm, which actually translate that plan into actual commands that we're going to send to the robot wheels. So we need to take this plan and we need to turn it into like, put the gas pedal down, put the brake down, turn the steering wheel. And those actuation commands get sent back to the robot. So this feedback loop is like the loop that's working on every single robot system, autonomous robot system. I've got this other box here, which is also kind of overlooked, but super important, which might play an essential role in making some of these things be easier or harder. And that's like generally referred to here as infrastructure. So there might be things in the world that we know about that we can leverage as priors or as like prior information that we can use to make the task easier, either the perception task, estimation task, or planning task. For example, GPS satellites are up there spinning around the Earth, and we're able to use the signals from GPS satellites to really help us with the localization problem. Maybe that tells us where we are on Earth. Like that's how our Google Maps thing or whatever works. So that's a good example of infrastructure. And this infrastructure is super important. So I've got this example of what I would conjecture is maybe the most impactful robot system in the world right now. So these are little robots that operate in the automated Amazon fulfillment centers, and they drive around and pick up the shelves and bring the shelves to people to pack boxes. And yeah, they're trying to like also solve the problem of automatically packing the boxes, but that's a much harder problem. But the thing that I find kind of interesting, or like, why is this system work so well? Well, the infrastructure and engineering of this environment is has been done specifically for the operation of these robot systems. There's these little markers on the ground that the robots use to localize. All the shelves are exactly the same. There's very few people or unexpected things that happen. This almost becomes close to an automated system. Where do robots have a lot more trouble is in environments like this, where there's an extreme lack of infrastructure. Yet you or I mean, maybe not the first time, but if we grew up in a place like this, we would have no trouble navigating this intersection. And actually, the efficiency of this system is extremely high. The throughput through this shared resource of this intersection is extremely high. So the role of the environment and the infrastructure has a huge role to play in terms of how easy or hard the rest of the downstream tasks are. Okay, I probably need to speed up a little bit. So we saw that different paradigm with all the different blocks. Well, now that we have machine learning, there's also other paradigms that have become popular or that are being explored. So one idea is, instead of all those different paradigms, we're just going to like drive the car around and we're going to let it figure out entirely the mapping from sensor data to control actuators at the output. And so this was an original sort of demo that came out from NVIDIA in 2016, which kind of blew everybody away, that like, actually, this is kind of possible to just train an entire autonomous driving system end to end. Now, there's lots of caveats there, but this is not as easy as it looks. Okay, so I have one question from the Q&A. In the autonomous driving pipeline, how to improve the perception model? Can we possibly replace LiDAR sensors? So the inclusion or not inclusion of LiDAR sensors is a debate that's mostly forged. So like, I don't want to get too in the weeds here, but so some of the folks who are pushing autonomous driving, who are trying to sell cars, people like Tesla, want to keep the price of their car low. LiDAR sensors are pretty expensive. Other folks who are pushing the development of autonomous cars are not trying to sell cars, but they're trying to sell a service. Like this applies to folks like Uber and Waymo. And for them, the price of each individual car doesn't really matter so much. And so they are more than happy to put expensive sensors on their cars. So can we replace LiDAR sensors with camera? It's a really open question, but my kind of canned answer for this is basically the problem's already hard enough. Why not use the best possible sensing that you have to get some of the things that you get from LiDAR for free, like sort of 3D geometry, are extremely challenging to get from just camera modality. And so by not having LiDARs, you're just making your life harder. But it's sort of unclear whether the LiDAR is like necessary or not. Okay, so another paradigm for learning, especially with data, is this idea of reinforcement learning. So the way the reinforcement learning system works is like really elegant in its simplicity. We just have some environments that the robots operate in, and we let them try stuff, and then we tell them how good what they did was. And so this is like kind of the way that we like train, I don't know, dogs. I was gonna say kids, but like that's a little bit, I don't know, kids do a lot more complex stuff. But like when you train a dog to sit and then give it a cookie, like this is basically reinforcement learning. So this is a nice idea as well. The problem for, say, something safety critical like autonomous driving is that we can't just like let this autonomous car just like thrash around and like mow people down on the sidewalk while it's learning how to drive. So, but some folks have also explored this paradigm. So this is a system that was mostly trained in simulation, and then basically every time the car drives off the road, it's like it receives like a negative reward. Or in fact, to be more precise, every time the safety driver takes over, the system gets a negative reward. And over time, it figures out that it just needs to stay on the road for longer and longer and longer in order to not get that negative reward. And this also is like sort of surprising that it worked at all to me, but it does work to some extent with caveats. Yeah, and then inside this reinforcement learning loop, there's also the role of simulation. So ideally, we'd be able to like learn a lot of what we want to know in a simulator. And now we have these like really high fidelity simulators that we can use for this task. But exactly how we leverage these simulators to learn is still very much open research questions. This is one particularly compelling example where this team from OpenAI trained this real robot hand to solve the Rubik's Cube. And this was like kind of a famous thing when it came out a couple of years ago. Maybe some of you saw it. The hard part is not figuring out which things to do to actually solve the Rubik's Cube. That we had figured out to do, many years ago. It's more about the fidelity of that hand and the way it's able to manipulate the Rubik's Cube. And this was trained almost exclusively in simulation, but then just fine-tuned on the real robot. But the simulation itself cost an awful lot of time and effort to build. So what's the balance between building a really good simulator versus training on the real robot? These are all like open research questions that I study in my lab. Okay, so I remember that the title of the talk was the AI Driving Olympics in Duckytown. So maybe we'll try and pull that thing in. So one super hard question with autonomous driving, but robotics in general, is how do we actually know how well we're doing? So like some of you, I'm sure like you've had science class and we talked about what it means to do science. And like to do science, the bar is pretty high. Like you need to have controlled experiments and hypotheses and things like this. But with robots, it's tricky because like robots are acting in closed loop. It's very difficult to separate the system out into some very controlled environment where it can be reproducible. Like, what would it even mean to have a controlled experiment on an autonomous car? Like, yeah, we can use closed loop tracks, but at what point is that actually representative of the big wild world that the actual autonomous car is going to be in? So just the question of evaluating how well we're doing in terms of building autonomous cars is not straightforward. the big companies who are working on this, they publish statistics like the number of times their safety driver had to take over per number of miles or whatever. But even that's not so straightforward, because like I could take a car and just drive up and down the road where there's nobody, and I could have a really good, I could hack those statistics really easily. There's this like Goodhart's law, which some of you may have heard of, that when the metric becomes an objective, it ceases to be a good metric. Okay, so and then there's some other things that I mentioned here. That robot tasks are highly complex. There's the variability of hardware. There's also lots of other dirty details about the system of robotics that are important. And so we built this AI driving Olympics as like as a sort of a very simple benchmark to try and evaluate things. Okay, so this AI driving Olympics, it uses this Duckytown platform, which I'll talk about in a second. And we ask people to submit agents that will be put onto these little robot cars, and then they'll be run on this like toy track. And we go to conferences and like build this track, and then we run all the agents on the track, and we like see who wins based on some metrics. So we used to do this like IRL, like in real life at NeurIPS and ICRA, which are some of the biggest machine learning and robotics conferences out there. And then this like COVID thing happened, and now we've started doing it more remotely. Okay, question. There are examples of pure reinforcement learning enabling a helicopter to learn how to fly. Can this be translated to autonomous driving as well? Is it feasible? Okay, great question. So I think there's like this interesting complementarity to something like the flying of a helicopter and autonomous driving. So on the one hand, a helicopter is a challenging dynamical system. It's got a lot, very complex dynamics, and the way that the control needs to happen has to be like very precise. And maybe the number of actuators that you have in that system is very high, and it's quite unstable. So like the major challenge for a helicopter is just to make it actually fly. Whereas for an autonomous car, the action space is relatively low dimensional. It's just the steering wheel and the brake and the pedal, and the dynamics of the car are not so complex. It's pretty stable in the sense that if you just like leave it stopped, it doesn't fall out of the sky. However, the environment that the autonomous car is operating in is like so much more complex than the environment that the autonomous helicopter is operating in. Presumably, the autonomous helicopter is just trying to fly and not crash. So it's not super clear. So like I think that reinforcement learning is more directly applicable to these kind of difficult dynamical systems that are hard to model, but that helicopter doesn't have a huge burden of perception to actually do the perception part and figuring out what's going on in the world. Whereas so it's unclear that for these very complex environments that reinforcement learning is going to be like expressive enough to really inherently build this model of the environment in some efficient way. I could say lots more about that, but I think it's the idea that you're going to be able to learn how to drive with purely just reinforcement is really putting a lot of burden on the like perception system to learn a model of the world from a very like low dimensional signal, which is the reward. Okay, I can talk more about that if there's more questions at the end. Okay, so what is this Duckytown thing? So we built this silly, fun like thing when I was a postdoc at MIT in, I don't know, like 2015 or 2016. So this is a class now that we use. We teach with this environment. This is the first class that we had at MIT. This is the original developers at MIT. Let's see, anyone that went to CMU here? I don't think so, but lots of these folks ended up being profs in various different places. We tried to have fun. Like, I think this was part of the point of this project. It's like, I don't know, it's supposed to be fun. And we like ended up having this like massive demo at the end of the year, where all the students like showed all the like capabilities that they'd made, and we build, this is like in a hockey rink, and we like build this huge thing, and like invited everybody from Cambridge and Boston to come and look at it. And we made the mistake of like giving everybody a little rubber ducky when they went in, and then like all you could hear for the rest of the time was just like squeaking duckies. So we also use this platform for research. I make this kind of like tongue-in-cheek kind of claim that although the scientific value of our little toy robot is slightly less than an autonomous car, the cost is dramatically less. This isn't meant to be like a serious claim, really, but there's something. And then we use this thing for this AI driving Olympics, which I'll talk about in more detail in a second. It's also an outreach effort. So this is a major motivation behind this project was that it would be low cost and accessible, and that people from all around the world would be able to use it. And so this is one example of, in 2018, one of my PhD students went to Ghana and taught a little high school robotics, I think not class, but like a 2-week intensive kind of thing to some students in Ghana. And so we very much view that this is meant to be something that's accessible for everybody. So speaking a little bit to like some of the objectives of this robo launch in terms of equity and diversity. There's also, maybe I'll make like one other comment here. There's like sometimes the perception that robotics is something that's big and scary and meant to be fast and powerful. And we're also trying to present something of an alternative, like an alternative model of what robotics could look like, as something kind of fun and not going to hurt you. Yeah, so we have all this code, open source, that now we can use for building this thing, and it's sort of like a kind of open source standard implementation of a lot of the basic robotics components. I sort of talked about this accessibility. It's now been taught in like high schools and universities. The platform's been used in various ways, like across the world. It's much more than this map now. I've sort of lost track of everybody that's using it. And maybe just before I answer the questions in the Q&A, I'll just give a little bit more precision about what the thing actually is. So our objective when we were trying to build it was to have like a low-cost robotic platform that we could still do interesting stuff with. And for us, interesting meant that it had some amount of compute that was more than an Arduino, and a sensor that was in some sense realistic, like a camera. And so we ended up with this thing that's costs a couple of $100, I think, at most. And we also co-designed the environment that it should operate in. And so the Ducky bot itself just has 2 DC motors, a camera, battery, and then some kind of like, we used to use the Raspberry Pi, and now we use the Jetson Nano. And then of course the Duckies are meant to be the like the customers in this autonomous like taxi service. So they're essential also. And then the town itself is like, although it looks kind of cute and is built out of like exercise mats and tape, is formally specified, like exactly where the sign should be, exactly the angles for the turns and how you should tape things. Like there's a floor layer that's composed of these tiles, and then a signal layer that has like traffic lights and signs. And yeah, maybe just one last comment. We actually released a massive online open source class on this thing. And so this is part of our like outreach effort and education effort related to this. So, okay, in the Q&A, I have 2 questions. Is it that we can't provide guarantees because we can explain our cognitive model to the world, e.g., yes, the accident happened because I got distracted and turned my head? Also, if we need to be able to build cognitive models, should we necessarily have to build a general vehicle for doing that, i.e. human brain? Or could we get away with a domain-specific one? What's your take on that? Okay, it's just a question from Misha. Sort of a lot to unpack there. The first thing that I would say is that the bar in terms of explainability that we hold our autonomous system, our systems to, is much higher than the bar that we hold people to. Like we are not comfortable with the idea that this safety critical system is going to act in some kind of unpredictable way, even if we might be kind of comfortable with the idea that there's some probability that a person is going to act in an unpredictable way. So it's tricky. Like there's an element of actually just education here about explaining the way that these autonomous systems are meant to act. And in some sense, the model of an autonomous system that behaves in a very reproducible way that people understand is somehow possibly more tractable in terms of integration into society. Like think of a train. Like if you walk in front of a train and it hits you, you don't blame the train, you blame the person. But we're still at the point where if somebody walks in front of an autonomous car and gets hit, it's a debate. It's like, well, the person was doing something they shouldn't have been doing, but the car should have reacted because a person might have been able to react. And so it gets really, really difficult. And so in terms of guarantees, it's like, it's very difficult. They're going to be probabilistic guarantees, not hard guarantees, but somehow we need to be able to like certify or verify that our system under nominal conditions is going to behave in some kind of predictable, reasonable way. In terms of modeling of the human brain, I think this is like a really tricky thing that I don't know that it's the right path to try and get to the point where we're reproducing the human brain. Yeah, maybe I'll leave that one there. Maybe if there's follow-ups, feel free to ask. There's the question about how the ducky cars are related to the F-110. Very similar in concept. The F-110 is meant to be kind of fast and race, whereas we were sort of more interested in building a system that could handle kind of more complex environments rather than just going like fast. And also the sensors that we're using on the F-110 are a little bit, they're cheaper. Like I think they have a LiDAR sensor on there so that they can do like the really fast racing stuff. But in some sense, really similar like kind of conceptualization. How DuckyBot PCB is different than Arduino board. So yeah, the DuckyBot has two boards. One is kind of very similar to what you would find in Arduino. We just custom built it. This is the thing that like drives the motors and drives the lights and stuff like that. But then in addition to that, we also have a computer like a Jetson Nano or a Raspberry Pi that is way more capable than an Arduino. You can install an operating system on it, and you can do like you can treat it kind of as like a full-blown mini computer. And this makes life a lot easier in terms of being able to use it and interact with it, because you can basically use it as if it was like a regular computer. The Jetson also has a GPU on it, which we can use for some of our machine learning stuff. Okay, so this AI driving Olympics thing, what is this? So a little while ago, I was talking about benchmarking. And so I've in my sort of academic life, I've been trying to think hard about how we can forge ahead in terms of this benchmarking effort. So one thing that we've done is we've held a couple of workshops at top conferences where we've gotten lots of people, smart people together and try and think about this problem. It's a very hard problem. But also we built this benchmark that we call the AI Driving Olympics. So, I mean, I think I may be running out of time a little bit, so I'll skip over some of the maybe unnecessary details, but like in the conceptualization of this AI Driving Olympics, we were really looking at a way to compare vastly different types of algorithms and agents in some very systematic way. So like now we have this traditional way of building robot systems with all those like components that I showed, like perception, estimation, but we also have these end-to-end approaches and reinforcement learning approaches. And so we just wanted to build some kind of like clean divide where we could evaluate agents, no matter what type of agent they were, in some systematic way. And so this is are like some of the scientific objectives for this thing. And also like the Duckytown project, we wanted it to be accessible and easy. So we built all the baselines for all these different kind of standard algorithms like the traditional one, imitation learning, reinforcement learning. We have a simple API that you can use to get started very easily. We have data, like, so you can build your agent, then you can test it locally. You can push it to our system where it gets evaluated on the cloud. You can push it to your robot and actually see how well it does on the robot, all in some very simple, with some simple API. We have lots of logs that people can use, some of which are annotated. We also have these remote labs, which we use for the real robot evaluations, where we have this like camera system that can localize things and evaluate things. I gather, because I'm seeing more people show up on the cameras, that I'm running out of time. Is that I should try and wrap up? Is that
Well,
correct?
actually, I'm going to let Rachel comment on the time, but I do have one question from the room for you, Liam, if that's
Oh,
okay.
great. Yeah, perfect.
Do you think, okay, great. Do you think self-driving cars will become safer if most cars on the road are self-driving? Is there any work involving a network of cars like a hive mind for city driving?
Yeah, that's a great question. I mean, I think one thing that I think is true is that if all the cars on the road were autonomous cars, that would be a dramatically easier problem in some sense, especially if all the cars were automated and there were no pedestrians. Like, the more we can take people away out of it, then the easier it gets. You get closer and closer to something that looks like that Amazon fulfillment warehouse where the cars are just driving around and can like, in some kind of very structured kind of environment. Yeah, that's the sort of catch-22, is that like, if we could just like flick a switch and get to the point where the entire transportation system was automated, that's actually an easier problem than going through the transition that we're going to have to go through to get there. In terms of vehicle-to-vehicle communication and communication with the infrastructure, I think this is also has a lot of potential and is relatively underexplored. One big problem that comes along with that, though, are like security risks. So as soon as cars are now subscribing to and like communicating with the infrastructure and with each other, now the burden in terms of guaranteeing that the system is not hackable is somehow higher than if you just have every agent operating independently. Yeah, I don't know if that answers the question fully, but those are my thoughts. And yeah.
Yep, I have a nod from the questioner, so that was good. Thanks.
Okay, great. Okay, so Rachel, how am I doing on time?
You're doing great. We have another group that's working with students, and I'd like to share their question, and maybe
Okay.
spend a few minutes talking about that. It's about career journeys and looking back, and for students at different stages, whether it's high school or undergraduates, how do they? When you look back, how are some ways that they could get started in robotics? And looking back at your career, what advice could you provide to students? And those are two different age groups, but high school or undergraduate students that are interested, they've learned a little bit about robotics and they want to dive deeper and see if they can explore careers in this area.
Yeah, so my personal journey was I was not someone who was like interested in robotics in high school or even really undergrad. In fact, when I started grad school, I wasn't really working on robotics, and then I just happened to get involved in this robotics project, this marine robotics project that I found super interesting, and then the rest was history. So, I mean, I think maybe the lesson to be learned there is like, you always have to be open-minded about you know, what interests you and what you're passionate about, because there's no one trajectory for every person. Some people know from the age of 5 that they love dinosaurs and they want to work on dinosaurs for the rest of their life. For some other people, it's a little bit more of a meandering journey, and I think I'm an example of that. In terms of getting started, I think just getting your hands dirty is the best way. So particularly, I would say more than ever, building up your skills in terms of programming skills that are going to those are going to really become the building blocks of what you're going to do. I mean, there's lots of different flavors of robotics. Some are much more hardware and mechanically like design aspects, but I would maybe this is my biased opinion because I'm a computer scientist, is that more and more of the hard problems are algorithmic problems. And that someone could really argue with me on that, but that's a debate that we could have. But there's certainly, I think you would not regret building and sharpening as much of your programming tools as you possibly can. And particularly like those kind of starting to program some systems that actually interact with the real world will give you some experience for that. And there's lots of different tools out there. I mean, so like obviously something like DuckyTown is one, maybe not exactly targeted at the high school environment, but those like Lego Mindstorms and lots of other robot kits that now have little APIs, little Python APIs that you can use to do cool stuff. So I mean, I think, yeah, if you're passionate about it, then go for it.
That's fantastic. Is diving in and being open and really that early exposure, if they can, to programming and building up that skill set, because it will go with you for quite some time. It'll go with you for quite some time.
Yeah.
I'd like to invite any of the so our facilitators that are here, if there are any last questions across any of the platforms, to share those questions either in the Q&A section or just to speak the questions.
Do you think that robots remove jobs? I know there's a lot of statistics saying the opposite, but I see less and less working in factories, et cetera. Okay, so this is a tricky one. One example that we could cite from history where I think there were the same fears, and these fears did end up being not really coming to fruition, is actually the case of the personal computer. So when the personal computer came on the scene, I think a lot of people were worried that jobs would get removed, and they were, truthfully. Like there's a lot of things that people used to do before the advent of computer that we don't do anymore because we have computers. However, there were a lot of different types of jobs that got created because of computers, and a lot of people's jobs got easier. So it's not so simple. I also believe that, yeah, as I said, like I think we do, I don't want to get like too political or philosophical, but we do need to think about building mechanisms by which such that the entire society reaps the benefit of automation. I mean, as it stands today, if a company is able to automate some component of its system, the people that benefit are the shareholders of that company much more than anybody else, because they're able to fire some people and presumably the robots work for cheaper. So yeah, I think it is something that we should consider very carefully from like at a societal level. But it should be, I mean, I think that it should be a good thing if we can automate things. It should be a good thing. And so we just have to make sure that we build the right mechanism so that it is for everybody. Okay, I'm not sure I answered the question. But which programming languages are most commonly used for robotics and AI? Okay, so I mean, in academia now, Python has become kind of the de facto standard for rapid prototyping. So I would say that that's, if you're gonna, and it's a language that's relatively easy to get started with. It's relatively user friendly, let's say. When you're actually going from like prototyping academic systems to the real fielded robotic systems, I think a lot of those become more like C++ and languages that are more strongly typed and have better guarantees around real-time performance and things like that. So I would say that C++ is also would be a valuable tool.
We have a student joining us. Will, would you like to ask a question?
Yes, I would like to ask a question. Thank you, Rachel. My question is related to your DuckyBot and DuckyTown. So what future initiatives do you have planned to expand your DuckyBot program to increase its positive effect locally in your community or globally? I'm just really interested to see how you want to progress this program because I feel like you have something really good on your hands with making such an affordable entry into robotics that could affect a lot of people. So I'm just curious on how you want to expand on that project.
Yeah, thanks for the question. I think that the biggest push right now, so as it stands, to interact with the project, you need to be able to use the Linux command line. You need to be able to write Python code. I mean, the barrier, like we're still at a level where it requires kind of some fairly significant basic knowledge in order to interact with the platform. And so I think that our push is going to be to really just continue to try to remove those barriers. So while I think that those things are important for a roboticist, it might not be necessarily important that you learn the Linux command line if you're in grade 10 and you want to get started on robotics. So it's a balance between showing all the mess and all the dirty details that are actually underneath versus abstracting some of that away in order to lower the barrier of entry and still have good pedagogical kind of outcomes. So we're pushing for building models where we can control the robot with iPhone apps and stuff like that, and not have to have a computer that runs Linux and have to use the command line and things like that. That's mostly the push right now.
I know that we're just a few minutes over our time together. There's a last question here in the chat. I'd like to see if you'd like to address that. And also, John, there's another student with a question. So maybe these are our last two questions to wrap up.
Awesome.
Sorry.
Okay, I'll start with the one in the Zoom. So
Okay.
As a mechanical undergrad, what should I focus on to have a successful career in robotics as it towards mechanical design, mechanisms and hardware, or should I dive into programming? So this is a little bit of a tough one for me to answer because this is not my particular background. So my gut feeling is that you won't regret sharpening your knives when it comes to programming, that now robotics is really about the interactions between software and hardware and the co-design of these things. But I guess in terms of mechanical design, it's about being able to do rapid prototyping and learning tools for rapid prototyping, I guess, to try out new ideas. But I would probably ask someone who's more in the mechanical side of robotics and listen to what they say is probably my best piece of advice.
Great. John is actually a mechanical engineer by training, so maybe he'll comment
John.
on that later. He'll comment on that later. Yes. So we have another question in the room. Would you like to go ahead?
Yeah. So you showed a video of humanoid robots earlier, and my question is, what are your thoughts on the Boston Dynamics robots? And they're not autonomous because they say someone is always behind the scenes controlling their movements, but what do you think about the direction they're going with their mobility? And would it be possible to make those autonomous? And what do you think that would be like if they were able to make their highly mobile robots autonomous?
Yeah, so I think that they are actually what I would consider to be autonomous. So I think they're amazing. That's the first thing to say. I think that what they've been able to do with their humanoid robots is it's kind of rare that I'm blown away when I see something in terms of a robot demo, but they are consistently able to blow me away in terms of what they're able to achieve with their systems. I'm not totally sure how, I think the major challenge for them is that a lot of the demos that they do are quite scripted in the sense that it's not somebody behind the scenes who's controlling it as much as it's been a kind of a completely scripted thing. It's sort of that the robot is following. So in that sense, it is kind of automated and not autonomous. But I know that they are moving towards doing more perception of the world and everything like that. Is that the right form factor for a robot that we want? Like maybe that was also part of your question. Like, is that the thing that makes our lives better? I don't know. Like what, like, yeah, maybe, but like, it's sort of hard to imagine that too many people would want like a 400-pound, robot in their living room, like vacuuming while they watch TV or whatever. So it's a tough balance. Like exactly what the use cases are for those robots, I think maybe a little unclear, but in short, I think that those are like Boston Dynamics have pushed the state of the art in terms of so many things related to control and to like fielding and deploying these systems that they're sort of way ahead.
Thank you.
Thank you. I want to
Awesome.
turn. Sorry, I wasn't quick enough. If it's
Sure.
okay,
I
please.
have time. If everybody
Okay,
else has time, I have.
Thank
Yeah.
you. Go ahead, please.
All right. So you mentioned that in your research, you're really interested in benchmarking autonomous driving systems. And one of the things I have as a question about that is when the systems are being developed, there's always a level of uncertainty and this sort of like fine-tuning problem to get everything to work in the real world. And generalization is a really difficult problem. But even just a small bit of error, when you start to put at this very large scale of, the entire world, will produce lots and lots of issues just from that small error. And so when do you see it sort of being adopted, this technology, and after the fact that, when is safety going to be safe enough, essentially? I want to know what will be the result. Like when do you think safety in cars will be safe enough?
Yeah, it's like a really, really, I think, hard question with no really good solid answer. In terms of, so the way that I see it going in terms of the integration of this technology into our society, like what we're already seeing is two fundamentally different paradigms. One is the paradigm of we're going to keep selling cars and then we're going to add increasing more and more and more autonomy to the cars that we sell. They're going to be able to drive themselves on highways and the other way is in a very restricted geo area where it's a mobility on demand service and you have an app and it comes to get you like a taxi. And so I view actually the progression for these two things to be kind of a little bit different. On the one hand, so like I think probably the like shortest answer to like how safe is safe enough is when an insurance company is willing to give you an insurance policy for it. Like it's really going to be something boring and dumb like that, right? Like right now, no company in that first model who's selling cars has been willing to accept responsibility if something bad happens. It's always been, the model is that it's up to the driver to be monitoring the system, and if something bad happens, it's the driver's fault. So for me, that will be the indicator that we're close, is when the first company says, if something bad happens, it's our fault. It's not the driver's fault. Or in the other context of the like taxi service, it's a little bit more structured. And so the size of the geographic areas that those systems will be deployed will sort of grow slowly. But yeah, in the taxi model, it's going to be more about like, okay, this is how the car behaves. And if you don't adhere to this contract with the way that the car behaves, then you should expect that then if an accident happens, it's somebody else's fault because they weren't following like the rules that we've decided around the way that these cars operate. So I think that there's not gonna be a way to like statistically say that they are safer. That is going to be very, very difficult. But maybe if I can add one other thing, I mean, I think people have to, so one problem, and I think maybe I'm going on like a bit of a weird tangent here, but stay with me for a second. So people are not super comfortable at calibrate or like able to calibrate risk in their own lives. It's like when we get into a car, there's an element of risk there. We don't think about it consciously because we've somehow accepted that risk. But there's some percent chance that every time you get in a car and drive somewhere that something very bad is going to happen. But the way that we evaluate risk when it comes to autonomous systems is different than the way that we evaluate risk somehow when we feel we have some control over it. And so the parallel that I like wanted to make, which is maybe weird, is like the evaluation of risk that we've done with COVID has also been like very difficult to calibrate, you know, like because very bad things can happen, then we've gotten very, very worried about them. And so, yeah, it's calibrating risk is one thing, but it's people's perception of that risk, which is also super important. And yeah, I know I haven't really answered your questions. I've just sort of like rambled on for a bit, but it's like, it's a very good question, like with no really good answer.
Thank you.
I'm pausing just
Ready to
for,
wrap up?
okay.
No,
Thank you, John.
there are no more questions from here. So thanks a lot, Liam, for the excellent talk and for the great job interacting with the question and answer, or during the question and answer period. Rachel, do you have closing remarks?
I again want to extend our thanks and turn it over really to Liam for the final wrap up. If there's a thought that you'd like to leave with the group here, we really appreciate you kicking this off. We see the excitement from the students, and we're looking forward to all the next steps. And I want to really thank the entire team here that has been instrumental in supporting and creating these opportunities. They've had amazing vision and drive. So thank you.
For me, I think just thank you for your excitement, like in this, you know, in this amazing field, and we need all of you to help make these systems become a reality. So in robotics, progress is might seem a little bit slower. So like don't just think that because you're like you can go and like do deep learning and that's all happening super fast. Like the development of robotics is slow for a reason. It's like slow and methodical. So you have to be patient and and do things the right way. But yeah, hoping to the next generation of robotics researchers being able to like solve some of these hard problems.
Fantastic. Thank you everyone for joining us today, and we look forward to continuing the conversation online. So take care.